Hello, Dr. Buzz here. Today we're going to be covering a topic that often confuses beginners to computational chemistry, which are tensors. Now, the name tensor sounds very scary, but I promise you it's really not that bad. So let's get started. So what is a tensor? You can think of tensors like multidimensional arrays from computer science. A scalar will just be a rank 0 tensor because you don't need any indices to access them, while a vector will be a rank 1 tensor since you need one index to access them. And a matrix, you can think of them like rank 2 tensors since you need two indices to access. And in a matrix, for each element, you need a row index and a column index. So from this example, A12 would just be the element circled. And notice how I use the computer science convention of starting from 0 rather than starting from 1. Now, there is no general name for arrays and tensors higher than 3 dimensions. Now, imagine that you have a rank 4 tensor called I. That means it requires 4 indices to access every element of I. And you can think of I as just a 4-dimensional block of numbers. Just don't visualize it, just take it for what it is. So, for example, you would need I, 1, 2, 3, 4 to access a specific element of I. Now, tensors would be useless if you can't really do anything with them. And tensor operations are just operations between tensors that result in another tensor. An example of this is actually matrix multiplication, where if you have C equals A times B, you have Cij equals sum over all k, Aik times Bkj. And matrix multiplication is an operation between two 2D tensors that results in another 2D tensor. And the matrix vector product is another example of tensor operations, believe it or not. Basically, it's an operation that takes a 2D tensor or a matrix and a 1D tensor or a vector and maps it onto a vector. Now, you can write it as B sub I equals sum over all k of Aik times xk. When we're dealing with tensor operations, we often like to leave out the summation and just write it like Aik times x sub k. And this is called Einstein summation notation. It's really not that bad. Just because it has the name Einstein in it doesn't mean that it's necessarily a difficult topic. But all this means is that the repeated indices are basically the index that's summed over. And most matrix operations don't have cool names like matrix vector product or so and so. An example of this is the J matrix build and the Hartree-Fock procedure, which is a first order approximation to the energy of a molecule. And here we have a JPQ equals IPQRS times DRS, which is the same thing as the sum over all indices R and all indices X of IPQRS times DRS, where DRS is the density matrix and IPQRS is the 2-electron repulsion integral tensor, and it is a rank 4 tensor. Now this may be daunting and hard at first, but I gave you some practice problems where you could work them out, and it could be and help you become more comfortable with this new concept of tensors. So I want you to convert each of the following equations from Einstein summation notation to explicit sums. And also, I'd like you to give the rank of each tensor in the equation. So for the first one, we have AM equals BMN times CMNP. And the second one, we have C equals APQRS times BPQRS. Now, pause this video and I'll show you the solutions. All right, so for the first one, A is a rank 1 tensor, B is a rank 2 tensor, and C is a rank 3 tensor. And to write it in explicit notation, it'll just be AP equals sum over M, sum over N, BMN times CMNP. For the second one, C is a rank 0 tensor, or if you recall, rank 0 tensors are just scalars, and APQRS is a rank 4 tensor, and BPQRS is also a rank 4 tensor. And to write it out explicitly, it'll just be C equals sum over P, sum over Q, sum over R, sum over S of APQRS times BPQRS. Well, that wasn't too bad, wasn't it? Just because something sounds scary doesn't mean it necessarily is. Well, have a great day, and I'll see you in the next video.